We shall start. Welcome to the first ZUCCMAP talk of the spring semester 25. I'm Marlo and this is Daniel, and today we're hosting Alex
Korocencev.
Thank you.
So Alex is a master's student at the ETH in physics, and he's been working on levitation and hoverboards since 2017. So he should have some expertise. And yeah, I think stage is yours, and enjoy the talk.
Hey, thank you. Oops. All right, so thank you all for coming here. As you have seen, the talk is about hoverboards, and I included the header Physics and Advancements of Magnetic Levitation. I always need to specify it because it happened to me in the past that I announced a talk about hoverboards, and some people came and unironically expected this. We don't have that. We only have the cool hoverboards today. Because, as you know, they're everywhere in science fiction and video games, and it's all around just seen as the futuristic technology. Especially if kind of the sci-fi writers are lazy, they just make everything levitate, even if it doesn't need to. But I would like to talk to you about how you can achieve levitation and why it is so difficult. So we start with two humble magnets. I'm sure all of you have played with those before. But yeah, if you try to create magnetic levitation with two magnets, like I have here, like yeah, you feel repulsion, but it's of course unstable. The upper magnet will always fall off to the side. So we can maybe do this. Done. Magnetic levitation. Except no, this is fraud. This is not real levitation. This is known as pseudo-levitation. Because in order for it to work, it needs to always touch some sort of mechanical support. So this does not count, unfortunately, even though it's still quite nice. We could maybe try to, okay, forget about the pole. Maybe we can stabilize it sideways using some more magnets. We could try to build something like this. And if this is in a two-dimensional universe, we try to levitate the inner magnet inside the outer magnet. I'm sure many of you have thought of something like this before. Hey, what would happen if we assemble it? Well, I made a simulation of what would happen. Does it start? Hello? Ah, yes. Even though it intuitively looks very stable, it really isn't. In fact, this assembly is just as unstable as what you see here. But okay, let's go one step more radical. Now we're talking. We put one circular magnet inside another fully encircled magnet and see if this will levitate. Remember, this is in a two-dimensional universe, and I want to ask you what you think will happen, whether you think it will levitate or not. I want you to raise your hand if you think that the inner magnet will levitate. Yeah, that's about a third of people. Who thinks it will not levitate? That's another third. Nice. All right, I will reveal the simulation in 3, 2, 1. Yeah, it crashes. Why does it crash if I try to simulate this? It's because of Maxwell's second equation. Let's try to draw magnetic field lines. The magnetic field lines going from the center, they converge in the middle, and they would form a singularity and a demagnetization force that would approach infinite. Because magnetic field lines, in order to be physically possible, always have to form closed loops. In this setup, in 2D, you can't have closed loops if you would try to build it, you would always have a defect somewhere, and then all the field lines would escape through this defect. And then, yeah, it would just get attracted to the defect. But we can say, okay, we have some theoretical physicists and mathematicians here. Forget about defects. We do it anyway. Well, as I mentioned, if we try to magnetize it without any defects, then the demagnetization force will approach infinite. So it will immediately demagnetize and fall apart due to gravity. So as you can see, it is quite difficult to levitate using magnets. And people from all over the world, like in China and in Europe, have tried actually for centuries to find any kind of array of magnets which allows the levitation of another magnet. And to this day, not a single array has been found. The reason is this: Earnshaw's theorem. It is a mathematical proof that magnetic levitation is physically impossible. Since we have a lot of mathematicians and physicists, I will talk a little bit about this. The only line that is very important here is this one. What this means is equilibrium in x-axis, equilibrium in y-axis, equilibrium in z-axis, summed up, must equal to 0. If you have a positive equilibrium, a stable equilibrium in the x-axis, that means you have a positive expression. If you have a stable equilibrium in the y-axis, you also have a positive expression. But because the entire expression has to equal 0, it must mean that in the z-axis we have a negative expression, which is equivalent to a unstable equilibrium. And the unstable equilibrium will make our setup kind of collapse every time. Every time we create a stable equilibrium, we must create an unstable equilibrium somewhere else. Like here, for example, we have a stable equilibrium in the height, but in the xy axis we have an unstable equilibrium, which has to be fixed with the pole. So we have proven that magnetic levitation is impossible. That's a bit depressing, isn't it? The way we go forward now is we look at our mathematical proof and we try to find loopholes wherever we can. And in fact, there are some ways to sneakily circumvent the mathematical proof. For example, the proof that I've shown you does not take into account that materials exist that have a negative magnetic susceptibility. Magnetic susceptibility is basically a material constant. It's a material property that every kind of matter has. It is a quantity that tells you whether matter absorbs external magnetic fields or whether it rejects magnetic fields outside of it. And negative susceptibility essentially means that we have a material that reflects magnetic fields, that expels magnetic fields out of its inside. The other exception is if we have certain dynamic effects. But let's start with diamagnetic levitation. As an example for a material that has negative susceptibility, you probably know about superconductors. Superconductors are basically, they have a susceptibility approaching -1, so they fully expel magnetic fields out of themselves, which allows for this kind of levitation that many of you probably have seen before. This is one of the most famous types of levitation. In fact, I have some superconductors, but there's a lot of hassle of bringing liquid nitrogen into Hage, so I didn't demonstrate it, sorry. But we have some other props. But the next thing I'd love to talk about is this effect occurring in materials that are materials other than superconductors. The physicists under you have probably heard about so-called diamagnetism. The simple explanation in semi-classical sense is we have an atom with electrons orbiting. We can say as a picture that we have electrons orbiting one direction and the other direction, kind of representing the sign of their moment of inertia. And if we apply an external magnetic field, some of the orbits get enlarged and other orbits get suppressed. And this in turn creates a very little dipole. So we have an opposing magnetic field generated by the atom. And in fact, many materials are naturally diamagnetic, like water, most organic materials, many metals, and specifically the, I always struggle with that word, pyrolytic graphite. Some of you may have seen this setup. This is a piece of graphite, and it levitates just like the superconductor that you have seen before. But you don't need to cool it down to superconducting temperatures. This is happening at room temperature. But unfortunately, this effect is a lot weaker. It's about 4 orders of magnitude weaker compared to the effect of superconductors. So the applications for a hoverboard are quite limited. You need a very, very strong magnet in order to levitate someone with that. But the good news is that, as I mentioned, organic materials are diamagnetic. So if you have a strong magnet applied to organic matter, you get many small opposing dipoles. So this is how the famous levitating frog experiment got performed. This is a magnet. Well, I forgot how strong it is. It's multiple Tesla strong. And just due to the diamagnets in the organic matter of the frog, you can, levitate it. If you make the field much stronger, you could also levitate a human like that. But that's not the most practical way to, for us to levitate, essentially. So we need to go back to the superconductors, where the effect is the strongest. The car company Lexus has used this effect to build a hoverboard a couple years ago. They put a bunch of superconductors inside a board. The superconductor inside the board is kind of submerged in liquid nitrogen, and you have a hidden magnetic track on the ground to generate the effect. Yeah, and later they jump over a Lexus car with it to the promotion. But yeah, this is actually one of the easiest ways to build a real hoverboard on which you can stand on, but it has certain limitations. For one, if you pause at the correct frames, you can see the magnetic track underneath. So if you use this to levitate as hoverboard technology, you will be constrained to a rail. And you have the issue that every couple minutes you need to refuel it with liquid nitrogen. Which is also not the most accessible thing, but it's still pretty cool. But what's even cooler is levitation using dynamic effects. One example that some of you may have come across already is so-called electromagnetic suspension. Here I have a prop that essentially does it. Yeah. What happens here is we have a very similar setup to this one, where we have 2 magnets. Here, those magnets attract this magnet, and then a set of electromagnets generate an opposing field. Statically, this arrangement would be unstable. This magnet, it would love to tilt and snap to the other magnets, but because there are sensors in here that detect the location of this magnet, it allows those electromagnets to compensate for the drift in location. So kind of those electromagnets, they're updated at least 1,000 times per second in order to keep this lower magnet centered, which is pretty cool, but it has the issue that it requires electricity to function, because if I unplug it, it immediately stops working. And also you have the issue that, as you can see, the equilibrium is quite weak in the setup. It's, a little sensitive. But with certain modifications, this technology has been used like as a fancy shoe display, and also actually in magnetically levitated trains. Some magnetically levitated trains use a variation of this technology in order to levitate. But now I'd love to talk about my favorite kind of levitation. This is the kind of levitation that I have spent by far the most time working on. You may have come across something like this at some point, that if you drop a magnet through a copper tube, it gets slowed down because the magnet induces electric currents into the copper. And those electric currents in the copper generate its own magnetic field that inhibits the motion, at least temporarily lets the magnet float. We can ask ourselves, can we use this technology in order to somehow levitate? And the answer is yes, we can. I would like to explain to you how it works, and we do this with a little physics exercise. I'm sorry. What we have here is a simple magnet, like this. And we move it with 1 meter per second over this sheet of copper. And we ask ourselves, what electric currents will it induce? We use the three-finger rule, and we see that here the magnetic field is entering the copper from above. You've got the magnet moving that way. That means that the induced currents will move towards us, out of the screen. On the other side, where the magnetic field is exiting the copper, we have the opposite. Here, we induce currents going backwards. So we have currents shifting here towards us, shifting away from us. And then we also generate sideways currents that kind of close the loop, so to say. Here's how it looks like in a real simulation. We generate two electric loops, two loops of circulating electricity. And as you know, electricity that goes in a circle generates a magnetic field. So we have an opposing magnetic field and an attracting one. And this doesn't do much here. It just gets slowed down a little bit. Where it gets really interesting is when we accelerate the magnet. Because if we move the magnet really fast, then we generate the current in front of us that creates repulsion. And then before this current decays, we force ourselves on top of that, therefore creating a resulting thrust upward. The way you would do it in reality is you would use an array of magnets, arrange it in a circle, something like this. You'd attach it to a motor and then spin it over a sheet of copper. So this is how it looks like in a simulation what will happen. So what you see is we have a bunch of loops of electric currents that generate magnetic fields that create repulsion. So those magnetic fields that are created from the induction, they exactly oppose the magnetic field arrangement above. So what one could do is one could assemble multiple of those disks and attach them to a bunch of motors and then put a battery on top of it. And then you could build essentially a hoverboard. Something like this, which I will now quickly demonstrate. And of course, when we demonstrate it, we have to recreate our own version of the levitating frog. Check. Here you go. And note, the levitation height is the distance from the copper to those spinning wheels. It's also additionally on some legs, but they're just here to not scrape the ground. Let's go. Oh crap. There you go. All right, let me safely unplug this. Unfortunately, I didn't have much space here because this is also kind of like a remote-controlled car. Like, you can steer it, actually, but it's very difficult to control because it's like ice skating on steroids. But here's a very similar setup where we simply have this very board attached to a rail to make it simpler to control, and then we move it up and down. Currently, there are 2 of those prototypes in existence that we have built. This one is a permanent exhibit at the University of Basel, so thank you to them for lending it back to me for the presentation. And the other one is currently in the Futurium Museum in Berlin as an exhibit. This is us who built it, and this is why we're putting it in the museum. This is me before my twink death, and and this is my friend Felix Sewing. We built this as part of for the Jugendforscht competition in Germany initially. But currently, we're working on further developing this very levitation technology for a different application. Because magnetically levitated trains are nice, but the market is not the best, if I'm being honest, because magnetically levitated trains live on government subsidies for governments that want to have a prestige project. So it's kind of, there are better markets to get into. So what we're doing is so-called magnetic bearings. Here's something that we have built. We create the same magnetic repulsion, but now we have a rotating axis that we stabilize on all sides by having repulsion in the entire XY plane. I need to thank for all the people who helped me build that, who made it possible, specifically Michael, Max, Toby, and Yves. Toby, who's in the audience. That's what we're currently working on. This is how it looks like in the simulation, where we have a magnetic array that is generating repulsion. Instead of from the ground, we just loop the copper around it. While this is a cool technology that is also functional, it is very difficult to pull off. Because in reality, you can't use a copper plate for that. You really need to use a copper coils instead. The reason is because you induce a lot of currents that you actually don't need. And this creates a lot of heat waste from induction heating. So if you build this magnetic bearing wrong, while you eliminate any kind of mechanical friction, you might generate more induction heating losses than as if you would have mechanical friction if you do it wrong. But the end goal is to essentially have it fully assembled, where we have two of those magnetic bearings that can properly levitate an axis very stably. And this has applications in fields like centrifuges, high-end pumps, like for example, helium pumps usually have magnetically levitated bearings today, actually. Also, in so-called flywheel energy storage, it is quite useful, where what you have is you have a mass, maybe a couple 100 kilograms, you rotate it very quickly, and this is how you store energy. It has mainly the advantage that you can charge and discharge the system without it degrading, even if you do it at a high frequency. But one application of such magnetic bearings that is actually was very much in the news recently is the following. You may have seen headlines in the past weeks that in Australia there has been a heart surgery where an artificial metallic heart has been implanted into a patient and then for 105 days until he received his donor heart. So 105 days, the patient had a robotic heart, and the heart worked so well that he was discharged from the hospital. He got to go home, actually, with this heart. What's special about this heart is, here's how it works. It's made by a company called Bivaker. I think this is how you pronounce it. It pumps blood, and the main rotating component is completely magnetically levitated. Because magnetic levitation has the advantage that due to no friction, you have a lot less degrading in the system, and also you don't have any contact points with no non-rotating components, so there's no opportunity for blood cells to get squeezed anywhere. And yeah, this Australian patient was for over 100 days. He had a magnetically levitated rotor inside his heart. So essentially, what I want to say is that the future of levitation, while it might have looked like this, we want to look at more like this. It will likely end up being more like this. So magnetic levitation is basically already here. It is increasingly coming into our day-to-day life, but mostly in terms of centrifuges, high-end pumps, some flywheels, and now apparently we have magnetic levitation literally in our hearts. Yeah, this was actually the main part of the lecture already. So I think I'm already open to the Q&A session. Thank you very much. Yes.
I have a question about, is there a usage in magnetic turbines or engines for a very fast rotating engine or turbine?
Yes, but the main issue is that often you would like to have your system rotate inside a vacuum for perfect performance. And usually you may run into some issues, like, for example, if you have turbulence, it is difficult to deal with because the equilibrium can be weak, at least weaker compared to a mechanical bearing. But yes, this has potential for engines, but more so for pumps that have a more controlled flow of gas or liquid through it. Yes?
I didn't quite understand the bearing in the heart. Does it still need electricity to run?
Yes. The patient, he needed electricity for it to run. And in fact, he had a cable sticking out of him where he could recharge the battery. But yes, that's the thing. You always, unless you're using diamagnetic levitation, you basically always need electricity in order to function. Because if it's no electricity, then, yeah, this. All right. Yes?
Are there any interference issues? Like if there are strong magnets nearby, do you get a heart failure?
I think yes. Yes, this is. You could maybe see it as an extra sensitive pacemaker. Yeah, so I wouldn't come close to a large magnet if I had this.
And another question.
Yes?
Like before you said that if you had this closed circle in a circle magnet, that you would create a singularity.
Yeah.
But does that mean no circular magnets exist like this?
Not in 2D. So essentially, if you want to see it in 3 dimensions, the equivalent would be having this experiment that I've shown before. Yeah, the presentation is way too large for my computer. Yeah, so the 3D equivalent would be if you had a sphere enclosed within another sphere. So if you wanted to repeat this experiment, you would have to build a sphere in reality. And there it wouldn't work. Just for simplicity, I use this instead, 2-dimensional universe. Because ring magnets can exist. Because in 3 dimensions, if I show the field lines can simply go around to the North Pole. So that's why we have ring magnets. All right.
And is it impossible with any 2 closed loops that are essentially the same, but one is larger than the other? Or it has to be perfectly symmetric with a circle?
Are you talking about 2D or 3D?
Let's do first 2D and then 3D.
Okay. No, because in 2D it is like if you would do this, you would have a bunch of field lines bunching up in the center. They would escape through a defect, and this defect would essentially correspond to a south pole. So here you have a north pole that is repelled by another north pole, and here you would have a south pole, so it would get attracted and touch the wall. So this is what would happen in 2D. In 3D, if you have a sphere within a sphere, the exact same thing applies. Interesting is if you say you have a ring magnet inside another ring magnet in 3D. Because what would happen in 3D is that you have a stable equilibrium like radially, in all radial directions, you are stable. But you would create a highly unstable equilibrium in the perpendicular component. So this magnetic ring, it would jump out or go inside. So it wouldn't stay fixed in the middle.
An MRI machine is essentially a ring to magnet, right?
Yes. But it's a ring in 3D.
Yes.
Exactly. Yes?
The main reason why this is an unstable configuration is because we cannot have magnetic sinks, I guess, like magnetic monopoles. But for the theory's sake...
Sorry, if I may interrupt. The fun thing is, even if we introduce magnetic monopoles, it would still apply. You can't levitate even if you would make magnetic monopoles, which is also fun. But yeah.
Okay,
Go,
that's what I wanted to ask. Like, if we were to assume that you could have magnetic monopoles and then take a limiting case to like where the magnetic charge, for example, would go to 0, what would then happen? But in that case, where it wouldn't even work if we would introduce magnetic monopoles, I guess that covers it.
Yeah, I mean, Earnshaw's theorem is pretty nasty, if I may say so, because it applies for magnetic dipoles, for hypothetical magnetic monopoles, if we could make them, and even worse, even if we say, okay, let's introduce electric charges, because it still won't work. Like people, before the proof came out, they saw, okay, we can't levitate a magnet above other magnets, so let's maybe try to electrically charge the magnet and use electric charges for our aid. But even that will always create an unstable equilibrium somewhere. Yeah, it's quite extensive. Yeah.
I guess a follow-up question, but regarding Earnshaw's theorem, does it apply to hypothetical higher dimension spaces? For example, if you could assume the space being 4-dimensional, and I mean, the Maxwell equations are theoretically n-dimensional.
Yeah.
What if you were to assume a 4-dimensional space or something? Would we still have the problematic cases for the ring in a ring magnet or sphere in a sphere magnet where it wouldn't work? Or this could n-dimensional space somehow allow for levitation in lower dimensional subspaces?
Okay. Short answer. I'm just an experimental physicist, so. Long answer. I would assume that it likely applies to any dimension, because kind of I did this proof kind of myself multiple times, and intuitively I would say if you just add more dimensions, it would still apply. Like here, it would end up with just having one term for one extra dimension.
If we would have like an even number of terms, for example, then the problem is that we have like one term that always kind of throws it out of balance. But if we have like an even number of terms, we could maybe offset this balance by another, I don't know, degree of freedom.
You mean kind of offset the equilibrium to another dimension, the negative. Yeah, but the thing is, then you're using an extra dimension for the same thing that this thing does, you know? You kind of, say you can generate force from that dimension, but you cannot move into that dimension. That's essentially what you do. So what I've done here is nothing else. I have a 3D system, and I've collapsed it down to a one-dimensional universe, like analog. So yeah, it's tricky. Okay, any experimental physicist-friendly questions? Yes.
I don't know if it's friendly, but you said that if the only case in which we don't need electricity for levitating to work is with diamagnetism.
Yes.
Would it be feasible for a diamagnetic heart to work, or would the diamagnetism of it all interfere too much with the organism?
You could very well have a diamagnetic heart. In fact, that would actually be kind of ideal because you could save a lot of power. The main issue is that diamagnetic materials, we have superconductors where the magnetic susceptibility is about -1, but making a superconductor inside an artificial heart is a non-starter. You can't do that. But the next best material, other than a superconductor that we know, is actually this specially manufactured graphite. But this one, I hope you could, yeah, here, has a susceptibility that is about -10⁻⁴. So the effect is like 10,000 times weaker. So maybe you could power the heart of like a fruit fly or something with it, but not the human heart.
But for the heart, it doesn't make any difference because, like, the heart needs energy to pump the blood around. So energy anyway.
But you can save a lot of energy because then you.
If you have a better pack, it doesn't matter if it's like small or big. Like, you do it anyway, then. How much?
And the fun fact is, if you didn't need electricity for the levitation itself, you only needed levitation for the rotation. Let's say hypothetically your heart stopped. You could pick up a strong magnet and do this and reanimate like that, even without any electricity. So yes, there would be some advantages. So thank you for asking.
Yeah, thanks everyone for coming. Thanks Alex for talking in such an engaging way. We have pizza waiting for you all. And of course you can ask more questions outside. You're gonna be around for a little bit more.
Yes, I mean first I'll probably start packing, but while I'm packing I can still answer some questions.
Yeah, so go ahead and do that. And next week we're also gonna have a talk at the same time, same place. It's by Alexander Pietak, and it's called a system to compress Lagrangian flows. So fancy compression algorithms coming up. Yeah, and I quickly wanted to ask how